Welcome to this explainer. Today, we're going to completely shatter the illusion of the perfect crystal. We're actually going to discover why tiny, microscopic, atomic mistakes are exactly what make our modern world possible in the first place. Make sure to keep your eyes on the slides as we go through this, and we'll keep these explanations nice and punchy so those of you reading the subtitles can follow right along. Let's dive in.
So I want you to start by picturing a flawless diamond in your mind. Or, maybe a pristine, gleaming sheet of polished metal. Really visualize it. Now ask yourself, is that material completely, flawlessly perfect down to the very last atom?
Well, the truth is, in nature, the answer is an absolute no. No real crystal is ever truly perfect. You see, at any temperature above absolute zero, the atoms inside a material are constantly jiggling and vibrating around. And this atomic jiggling guarantees that imperfections aren't just common, they're actually thermodynamically inevitable. It turns out, nature literally demands a little bit of chaos.
All right, moving into Section 1, Missing and Wandering Atoms. To wrap our heads around point defects at the absolute smallest scale, I want you to imagine a beautifully, perfectly tiled floor. Every single tile is exactly where it should be, but suddenly you notice a missing tile, or maybe you spot a tile crammed into a really tight corner where it definitely shouldn't be. Think about how that changes the integrity of the whole floor. That is exactly what happens inside a crystal lattice.
The most basic flaw we see is called a vacancy. Simply put, it's just a latticite where an atom is entirely missing, just an empty space. But rather than weakening the material in a bad way, this simple missing atom is actually a vital feature. It gives the other atoms room to move, which dramatically helps atoms diffuse through the material, and it totally changes its electrical resistivity.
Now, these wandering atoms generally fall into two really fascinating types. First up, we have a Schottky defect. This is when a pair of atoms, specifically a positively and negatively charged ion, just goes missing together. It's kind of like a couple quietly sneaking off a dance floor hand in hand to make sure the room stays electrically neutral. On the flip side, we have a Frenkel defect. This happens when a smaller atom gets bumped from its normal spot and shoved into a tight, irregular little space nearby, leaving a vacancy behind it. Both of these zero-dimensional defects fundamentally alter how a material behaves.
That brings us to Section 2, the secret to bending metal. Let's step up to a slightly larger scale here and think about a real-world situation. Have you ever wondered why you can take a regular metal paperclip and bend it back and forth without it just immediately shattering like a pane of glass would? Both are highly structured materials at the atomic level, right? So why does the metal yield while the glass breaks? The secret doesn't lie on the metal's perfection, but in its microscopic, one-dimensional misalignments. We call these dislocations. What we're looking at here is an edge dislocation. Notice that extra half plane of atoms squeezed right into the crystal grid. To really build your intuition on how this works, imagine a massive heavy rug lying flat on the floor, but it has a wrinkle in it. Instead of trying to awkwardly drag the entire heavy rug all at once, you can just push that single wrinkle across the floor until the whole rug shifts. This edge dislocation acts exactly like that moving wrinkle. Pushing this tiny flaw through the crystal is the primary mechanism that allows metals to permanently bend, which engineers call plastic deformation, without snapping in half.
Then there's another fascinating one-dimensional flaw called the screw dislocation. This one is caused by shear stress, a twisting force that literally twists the planes of atoms into a continuous spiral staircase pattern right along the defect line. Just like the edge dislocation we just talked about, this helical slip allows the metal to deform and absorb stress rather than violently shattering.
Which leads us perfectly into Section 3, boundaries that build strength. Okay, so we've seen missing atoms and we've seen moving atomic wrinkles. But what happens when entire crystal grids, moving in completely different directions, just crash into each other? Because most materials aren't just one giant continuous crystal. They're actually made up of lots of microscopic crystal grains pushed together. A grain boundary is this two-dimensional interface that forms right where two of these mismatched high-energy crystal regions collide. The atomic bonding there gets totally distorted simply because the grids just do not line up perfectly.
Now, we could absolutely get bogged down in some heavy math right now, like the Hall-Pitch relationship, but honestly, let's just visualize how this works. Think of these grain boundaries as solid brick walls. When those moving rug wrinkles or dislocations try to slide through the metal, they hit this mismatched wall and stop dead in their tracks. This brilliantly explains why creating materials with lots of smaller crystal grains and therefore way more boundaries actually makes a metal physically stronger and harder to bend. But there's a catch. Because these boundary areas are highly stressed and full of energy, they also become prime targets for chemical attacks, like corrosion, all while acting as fast-track highways for atomic diffusion.
All right, let's pull all of this together in Section 4, Why Imperfections Matter. You see, far from being annoying little flaws that we need to eliminate, these 0, 1, and 2-dimensional deviations from perfection are the exact tools engineers use to manipulate the world around us. By controlling vacancies, or intentionally adding dislocations, or changing up the grain sizes, we can tune a material's mechanical strength, completely change its electrical resistivity, alter its optical properties, or totally control how it reacts chemically.
Ultimately, imperfections aren't mistakes at all. They are the vital features that give materials their very properties. That right there captures the absolute essence of material science. Think about it. If a crystal were truly 100% flawless, without a single vacancy or dislocation, it would be so incredibly rigid. It would be impossible to forge into tools, practically useless for engineering, and quite frankly, entirely boring. So, as we wrap up this explainer, I really want to leave you with something to ponder. We all spend so much time chasing absolute perfection in our lives. But if the fundamental laws of nature actually rely on literal mistakes and flaws to build a stronger, more flexible, and infinitely more interesting world, well, perhaps perfection is highly overrated. Thanks so much for learning with me today, and keep questioning the flawless.